All right, welcome back. We're looking at section 4.3, dimensions of a vector space. So let's get started. So we have theorem 9, which is if a vector space V has a basis B1 to Bn, then any set in V containing more than n vectors must be linearly dependent. And like, that makes sense just like geometrically. If we have like R2, and so our basis for that can be like our elementary vectors 1, 1, and 0, 1. And so if we just have like another vector happening, that means that we have more vectors than we need, and this is so the set of all three of these vectors is linearly dependent because we can construct this one using linear combination of our horizontal and our vertical components. So yeah, when we don't need more. If we have more vectors than we have in our basis, then it's going to be linearly dependent set of vectors. Now, a vector space with a basis of n vectors, then every basis of V must consist of exactly n vectors. So we can't have too many, but we also can't have too few. And that makes sense because when we have a basis, like let's say that we have our basis 1 is basis of n vectors, and basis 2 is any other basis that's not of like this specifically n vectors, but they're both bases of V. Well, B1, this is going to be a basis, and B2 is also a basis, and they're linearly independent. B2, the set of those vectors, is linearly independent. So that also means that B2 has no more than n vectors because of what we were talking about up here with theorem 9, that we have, if we have too many vectors, then we have linear dependence. So in order for B2 to still be a basis and linearly independent, then we have no more than n vectors. And since B2 is a basis and B1 is also linearly independent, then B2 has exactly, or at least n vectors, but in order to be a basis for V, it has to have exactly n vectors. So B2 also is exactly n vectors. About dimensions, so if V is spanned by a finite set, then V is said to be finite dimensional. And we can say what the dimension of V is, and we write that as dim of V. That's the number of vectors in our basis. So what we were looking at before was n dimensional. So the dimension of our vector space up here was n. So it's finite dimensional because we're saying that n is not infinite. Okay, but we can still have if we have the dimension of our vector space, our zero vector space is going to be 0. So so it's possible for the dimension to be 0. And if our vector space V isn't spanned by a finite set, then we call V infinite dimensional. But so the dimension we write as dim of V. So pause the video, think about how you're going to find the dimension of the subspace defined by H, where A, B, C, and D are all real numbers. In subspace, we can write it, we can represent this with the linear combination of these vectors, where we have let's call it 1, is our coefficients of our A's, so 1, 5, 0, 0. Vector 2 is going to be our coefficients of our B's, -3, 0, 1, 0. B3 is our C's, so 6, 0, negative 2, 0, and sneak over to write our last one. V4 is our D's 0, 4, negative 1, and 5. So we have 4 vectors, and this is what's gonna span our subspace. But how are we gonna figure out, like, is there any repetition or any linear dependence within this set of vectors where we can eliminate one and still have a basis for our subspace? And I think so. If you look at V2 and V3, V2 is equal to V3 if you multiply V2 by what, negative 2? And then, so then we can get rid of like V3 and still have our, like fully span our subspace. So the dimension of our subspace is how many vectors? 1, 2, 3, in order to have our basis. So our dimension of this subspace H is going to be 3. The subspaces of R3 we can classify by their dimensions. So a 0-dimensional subspace is just your 0 vector. You can't get out of that. Your 1-dimensional subspace is a subspace that's spanned by a single non-zero vector, so a line that's through the origin. In order to be a subspace, it has to include 0. Right? 2-dimensional subspace is when you have 2 linearly independent vectors, so you're getting a plane, but it still has to be through the origin in order for it to be a subspace. And your 3-dimensional subspace of R3 can only be all of R3 because we have 3 dimensions in R3. So any 3 linearly independent vectors of R3 is going to span all of R3 from our favorite gigantic theorem, the invertible matrix theorem. H be a subspace of finite dimensional vector space V. Any linearly independent set in H can be expanded if necessary to be a basis for H. And also, H is finite dimensional, and the dimension of H is going to be less than or equal to the dimension of V. Our basis theorem, where we have V is a p-dimensional vector space, where p is at least 1. Any linearly independent set of exactly p elements in V, our vector space, is automatically a basis for V. And any set of exactly p elements that spans V is also automatically a basis for V. And the dimensions of our null space of A is the number of our free variables in our equation AX equals our 0 vector. And the dimensions of our column space is equal to the number of pivot columns in A, which is just a refresher. So, how can we find the dimensions of the null space and the column space of this A? Pause the video, try to do it. Null space, what do we need to do? We need to have our augmented matrix A and our 0 vector. And so when we ref that, what are we going to end up with? I want to pause so I don't just bore you, but I'm going to write it down. Have our row-reduced version of our augmented matrix with A and our 0 vector in order to find our null space. And so how many free variables do we have? Because the dimensions of our null space is equal to the number of free variables. So we have free variable of x2, also x4, and x5. So the dimension of our null space of A is going to be 1, 2, 3. And I guess we don't need parentheses, according to the book. So we reset. Okay. And then, how many pivot columns do we have? Well, those are the not free variables. So we have 1, 2 pivot columns. So the dimension of our column space is 2. Look at these two true-false questions. So if the dimension of V is P and S is linearly dependent subset of V, then S contains more than P vectors. Is that true or false? So what if we look at the 0 vector? Right? The dimension of that is going to be 0. And so that's just exactly one vector, but it is still dimension 0, so false. Right? How about number 2? If S spans V and T is a subset of V that contains more vectors than S, then T is linearly dependent. What do you think? True or false? The spanning set theorem, then S has a basis for V, right? If S spans V, then S has a basis for V. So we just have that, and then T is going to contain, so if T has more vectors than S, S's basis, then T is going to be linearly dependent because of Theorem 9 that we had very at the beginning. So this is going to be true. Alright, so what do we think about? We thought about dimensions of our different spaces. So we have the basis theorem for how many for our sets of our vectors that are forming a basis. We have the subspaces and finite dimensional vector spaces dimensions. The dimension of your vector space is going to be greater than or equal to the dimension of your subspace. We looked at some pictures of what that means. We found dimensions of our subspaces, looking at how many vectors were needed in order to form our basis, because that's our dimension. And we looked at how many vectors we needed for a vector space for a basis of our vector space. And when we have too many vectors, then we have linear dependence in that set of vectors. Alright, that just about does it. Bye.